Hello, my name is Jordan Miller, and this is Triangle Theory by Jordan Miller and Louis Cofone. Triangle theory proposes that the fabric of reality is not smooth and continuous, but made of a rigid, discrete mesh of permanently connected triangular units. These triangles do not stretch, bend, or break individually. Instead, all physical behavior emerges from how the mesh flexes, twists, and folds. Matter, gravity, and magnetism, and even fundamental particles like electrons arise as geometric features within this mesh, such as stable knots, curvature, or twisting patterns. This framework offers a new way to model space, energy, and quantum behavior using purely geometric and topological principles. Principles of triangle theory. Triangle theory proposes that reality is made of a continuous mesh of rigid triangles connected edge to edge, or vertex to vertex. The triangles cannot stretch or break, but the mesh can bend and twist through angular changes at connections. Three fundamental forces: weak attraction, strong repulsion, and bonding govern how triangles interact. Matter, energy, and forces emerge from patterns of curvature, vibration, and stable twists in the mesh, making particles and fields geometric features of space itself. Mesh structures and states of matter. In triangle theory, states of matter arise from local configurations of the triangle mesh. Solids are formed by densely packed edge connected triangles, creating a rigid, low flexibility lattice. Liquids maintain connectivity but with increased vertex based bonds, allowing flow through angular reconfiguration. Gases consist of sparsely linked triangles influenced primarily by weak attraction, enabling large-scale freedom of motion. These, m- these macroscopic phases emerge from microstructural connectivity patterns and intertriangle forces. Without requiring continuous fields, matter is geometry in motion. Emergent forces. In triangle theory, classical forces emerge from geometric deformations of the mesh. Gravity is results from large-scale curvature in, induced by mass, modeled as angled defects around vertices. Akin to Reggie calculus, arises from coherent twist patterns within regions of the mesh, generating directional influence through topological flow. These effects require no fundamental fields. Forces are manifestations of distributed angular tension and localized energy gradients. Within the mesh, this framework unifies interaction and geometry, making all forces emergent from structural behavior. Fundamental particles as mesh patterns. In triangle theory, fundamental particles are modeled as stable topological configurations, localized twists, knots, or curvature defects. Within the triangle mesh, these patterns store bending and bonding energy, giving rise to properties such as mass, charge, and spin. Particle identity is encoded in geometric structure. Different twists, symmetries, and connection topologies yield distinct quantum states. Rather than point like objects, particles are emergent from the mesh's internal geometry, behaving as persistent quantized excavations of space itself. Wave propagation, sound. In triangle theory, sound arises from collective oscillations of bonded triangles with dense mesh regions. As triangles flex at their connection angles, local deformations propagate as discrete angular wavefronts through the mesh. The speed and behavior of these waves depend on mesh stiffness, bonding density, and topology. In low density or weakly connected regions such as vacuum, wave transmission fails, naturally explaining the absence of sound in empty space. Thus, acoustic phenomenon areas are modeled as quantized geometric vibrations rather than classical pressure waves. Weak attraction force. The weak attraction force in triangle theory models a long range, low magnitude interaction between all triangles, analoged to gravitational potential at the substratal level. It acts across large distances within the mesh, ensuring global cohesion without introducing local bonding. This force becomes dominant in low density regions, preventing complete mesh fragmentations and enabling large scale structure formation. Mathematically, it scales inversely with distance contributing to the background connectivity of space without affecting short range particle stability. Strong repulsion force. The strong repulsion force in triangle theory operates as a dominant short range interaction between closely packed triangle nodes in the mesh, responsible for maintaining discrete particle boundaries and preventing geometric collapse. This force scales exponentially with proximity, generating a high gradient repulsive field that stabilizes the mesh density at critical thresholds. It is anisotropic in behavior, responding dynamically to local orientation and angular deformation, thereby enforcing structural rigidity and emergent mass. At the subparticle scale, this repulsion underpins the impenetrability of mass and facilitates the formation of stable patterns interpreted as fundamental particles. Bonding force. The bonding force in triangle theory is a highly localized elastic interaction that binds adjacent triangles at specific edge or vertex junctions, forming the continuous structure of the mesh, acting only at near zero separation. It ensures topological cohesion while allowing limited angular flexibility, enabling the mesh to bend without breaking. This force functions analogously to discrete versions of the strong nuclear force. Short range, high strength, and saturation, stabilizing local triangle arrangements into persistent geometric configuration. It underlies the mesh's ability to encode structure, transmit energy, and maintain the integrity of matter across all physical states. Fundamental properties. This is the weak attraction force. It models a gentle, long-range force that keeps distant triangles slightly pulled towards one another. The force scales with mass and weakens with distance, ensuring mesh cohesion across space. This is the strong repulsion force. It acts sharply at short ranges, preventing triangle overlap or collapse. This inverse fourth power makes it dominate when triangles get too close, enforcing geometric exclusion. This is the bonding force. It activates only at extremely close distances, locking triangles together into stable mesh structures. The high exponent, 25, ensures that the bond only forms at near perfect alignment, making it strong but highly localized. This is the charged particle interaction equation. It determines attraction or repulsion between an energetic particle and a triangle based on their energy levels. The function Fe1, E2 changes behavior depending on whether E1 is low or high, allowing charge dependent effects. This next equation, this this equation estimates the energy stored in an electron like triangle particle. It depends on the particle's radius, r, and its rest mass, m. The R3 term reflects how energy increases with volume in a 3D structure, while 10m accounts for intrinsic mass energy. Triangle geometric and bending. Key concepts. Each triangle is defined by 3 points in 3D space. x1, y1, z1, b is x2, y2, and z2, c is x3, y3, and z3. These are the fixed corner coordinates of the triangle. The triangle's edges are AB equals B minus A, BC equals C minus B, CA equals A minus C. These vectors define the rigid sides between vertices. The surface orientation, normal vector, is n equals AB times AC. The cross product gives a vector perpendicular to the triangle's face, defining its direction in space. The bending angle between two connected triangles. This is the bending angle. This calculates how much two adjacent triangles are bent relative to one another. This is the bending energy stored between triangles. K is the mesh stiffness constant. This equation measures how much energy is stored in the bend between triangles. This is a this is a triangle particle model. This is an electron example. This is my estimate of what an electron would look like in a triangle. The bending angle, zero bend, equals 70 degrees, and the bending energy, E bend, equals kx zero bend to the power of 2. Energy transfer between triangles. Energy triangles get energy from charged triangles. They spread their energy to other uncharged triangles until there is equal energy through all of them. Eventually, these charged triangles will stop spreading energy because the energy is equally spread out amongst these triangles. Thank you for watching this video. I hope you learned something about my triangle theory that me and Louis created. If you want to know more about it or more advanced details, then look at the Google Docs link in the description. Thank you. Bye.